Oh, hello. Welcome back to another session of Learning Glass. Let's open up another chapter in our discussions. So today we'll talk about solar and terrestrial radiation, how the Earth and the Sun get in balance with each other. So the ultimate source of all energy in our earthal terrestrial system is energy being radiated across the galaxy to Earth from the Sun. So the solar energy coming in, we are the terrestrial, not extra, but terrestrial. There's a balance between the energy coming in by the mechanism of radiation at different wavelengths of energy, of wavelengths of different, across the whole spectrum coming in from the Sun, and there's a balance where that pretty much determines our whole situation in terms of weather, temperature, life, or not life. So here's the Sun. It's doing its thing, and here's the Earth, not to scale, of course. And so if this is the Earth, and it's oriented towards the Sun like this, what happens is the radiance from the Sun goes in all directions as both are spheres, the Sun and the Earth. But on approach to the Earth, this incoming radiation is coming in, and what happens is we have an atmosphere of gases, that blanket. It's a cloud of gases containing clouds and gases that blankets the Earth, and that is an important thing for all life, all natural balance on the planet. And what happens is some of it gets reflected off of this radiation by the different sources of reflection, and then some of it stays in, because even though it might get, it goes in the direction from the surface towards space, but it stays because of the atmosphere. So this is just a general diagram saying that energy comes in through spectral radiation at all wavelengths, because the Sun emits at all wavelengths. I mean, the shorter than long, a big range of wavelengths. Not all wavelengths, but a big range starting from the small side. And so that's coming in, and then by different mechanisms from different materials, interactions in the atmosphere and on the surface, some of it leaves back to space by reflection, and then a fraction of it, of the energy balance, stays in the atmosphere Sun systems, the atmosphere Earth system. So this is the surface of the Earth, this is the atmosphere of the Earth. So within this system here that I drew the dotted lines around, there's some net energy in terms of not all of it leaves. And then in terms of the geometry of the Sun's orientation with the Earth, you can picture that if the Earth is being irradiated by the Sun, this would be the cross-sectional area. That is 4 pi r squared, where r is the radius of the Earth. Radius of the Earth, the cross-sectional that is facing that the sun sees a circle from its perspective, and that cross section is this here, but there's a hemisphere, so the surface area is pi r squared. So geometrically, there's a ratio between the cross section, like flux coming towards the Earth, and the actual surface area. So, well, that's important for this energy balance. But moving on, one way to understand the nature of the energy balance would be to describe this in terms of black body radiation. So black body radiation is kind of like a curve fit that is kind of empirical, but lately, since it's been developed over 100 years ago, there has been a lot of theoretical details on why this works. But over 100 years ago, a scientist named Planck, he did some experiments to quantify that all bodies emit thermal radiation in terms of some emissions from the surface of their body, and Planck was able to quantify that you can define this spectral irradiance where this black body radiation, call it FB, as a function of the wavelength of the energy, it can be infrared or below, or like, you just have to specify which wavelength you are. He fit that it depends on the speed of light, the Planck's constant, over the wavelength to the fifth power, and then there's this big exponential relationship where you get the temperature. So he was able to fit this to the Boltzmann constant, the wavelength, and the temperature, -1. So this big monster there, that expression, was fit to show that the intensity of the radiation coming off, this flux of spectral radiation, depends on the temperature and the wavelength. The rest are constants. This is the speed of light, Planck's constant, Boltzmann's constant, speed of light, Planck's constant. So it's a function of wavelength and temperature only, and it's a way to relate black body radiation to temperature. Then another simple yet very powerful relationship is the Stefan-Boltzmann way to quantify heat flux by radiation. So let's just call it heat flux for radiation. Heat flux, meaning watts per meter squared in terms of energy radiating, equals simply proportional to the power of exponent of 4, where this is the Stefan-Boltzmann constant. And then there's an emissivity that also can be used as a proportional, but let's just say that this one for now. So these are two ways to quantify the energy coming either from a black body source or from some radiation waves, whatever the wavelengths are. You can quantify the heat flux proportional to the temperature raised to the 4th. So those are two fundamental relations we can use to quantify this balance here. And the reason why these are useful, one reason why, is because if you were to measure the energy from the sun, which has been measured, you can plot something that looks like black body radiation. So if you were to say that the wavelength of light that I can measure in micrometers, let's say this is 2,000 nanometers, 2 micrometers, down to 400, the visible, kind of like the going into the UV, ultraviolet range. What comes to the top of the atmosphere from the sun it has a known shape in terms of wavelength. So let's say that this is 2,000 spectral irradiance is how it's typically called. It's saying that across the different spectrum of wavelengths, you have this intensity of energy coming in, this light, and it's typically described in terms of watts per meter squared, energy flux, divided by the wavelength as well. It's micron. So for each micron, it has a certain intensity. And the shape that's been measured looks like this. You know, it goes up and down because of the interactions with the atmosphere. So the detail, there's a lot of features in there depending on, because of the atmosphere and the interactions that occur with Earth, but it looks like that, somewhat, my artist rendition. So this black body law comes in handy because if you were to curve fit this Planck's law with the measured spectral irradiance of the sun, this emission power, it'll look like this. So this would be the measured sun radiation, and this would be Planck's law for a black body with an emissivity of 1 at all these wavelengths, across all these wavelengths, for a black body equal to about 5,777 Kelvin. So you may have heard the temperature of the sun given this value, and it's a good consistent value because the sun emits at all wavelengths, and this is one of the solid bases to provide evidence that the sun, to give a quantitative estimate of the sun. We don't have thermometers on the sun, but we do have physics of the universe. This is one of them. So by this curve fit to the data of the known measured radiance coming at us, we can deduce that the temperature is about 507.77 Kelvin due to this known emission that we get. So that's one thing, that's interesting. Then, if we were to integrate this, so this is as a function of wavelength, and so if we were to integrate Planck's law, we would say that the black body flux from the sun equals the integral of all wavelengths from 0 to infinity of this black body function of this, the area under this curve, for all wavelengths. So this is a known shape. We're fitting it to the data, and we take this area under this curve. That will give us watts per meter squared. And when we do that integral, it's about 1370 watts per meter squared coming in from the sun. So we call that the solar constant, meaning this is a good value to quantify how much energy is coming from the sun. If we have a square meter, there's 1370 watts per meter squared coming in based on this black body analysis. So let me start erasing stuff. Or should I? Let's see. So let's go back here. If we look at this geometry here, though, if this is all coming to the top of the atmosphere from the sun at this S naught value, 1370, what's actually coming in, so the ratio of the cross-sectional area to the surface area, so only 1/4 of SO reaches the surface, or is received 1/4 of the solar radiance, radiance constant. This is just a geometry. The ratio of this to this. So it's 1/4. So this gives us about 342 watts per meter squared, based that it's only coming in at a hemisphere, and even though the sun sees a circle of this, this is a cross-sectional area of the circle, only 1/4 of that gets felt by the surface. Okay? So that's a geometry thing. Next, let's talk about this reflectance. So this atmosphere has molecules, it has water vapor, it has particles. There's CO2 molecules, there's air molecules, and there's water molecules in the gas and the solid form. So the clouds, just based on their color and their optical properties, in a large part, they reflect. They're one of the reasons why energy from the sun gets reflected back into space. So because of the sun, the clouds, so fraction replacing back to space, that's called albedo. The symbol is typically RP. I don't know why RP, but reflection. So for because of clouds, that's a reflection net reflector. Depending on the molecule in the atmosphere and the cloud around the Earth, that can reflect back. Particles, some particles in the atmosphere, aerosol can cause reflections back. And the surface, depending on the nature of the surface, like ice, glaciers, water to some extent. So because of all these, and of course it depends where you are on the Earth, there's more ice in the caps, the poles, and clouds at different areas. So the global average, let's just say, it's like RP is typically 0.3. Let's just put a number that we're going to use. 30% of the solar constant that we see gets reflected back. That's a value that has been used, and we're going to use it. But of course, as you can imagine, depending on all the factors, depending on where you are, depending on trends from human and natural sources, this can fluctuate in terms of reflection back. And so what that means is the fraction absorbed by Earth and the atmosphere is what's left over. It's whatever is not reflected back gets absorbed by this system containing the cloud of gases, the blanket of gases, and the surface of the Earth. That's the 1 minus RP. And remember that this is all from a certain known profile of light coming in. It's from the UV to the visible to the infrared, not too deep into the infrared. So you can generalize it as relatively short waves coming in, and we'll talk about why we can call them short waves. So this is coming in from the sun in terms of these short waves. If we take the integral and we can get across this area under this curve, that gives us 1370 for the solar constant, but by the geometry of the circle that faces the sun, only 1/4 of that comes in as our input. 30% of it or so that we're using now gets reflected back. So what gets absorbed in from these short waves coming in is 1 minus RP. Okay. So typically a value, if this is so if we're saying that 30% it gets reflected back, so okay, so what's 70% of this? Well, 1 minus RP, that would give you at the top of the atmosphere 235 absorbed by this system there. Okay, so another thing that happens, another part of this interactions here, is that this is the profile of energy, spectral irradiance coming from the sun, but once it interacts with these bodies here, it can be clouds, molecules, particles on the surface. So only 30% reflects back, but the rest of it gets absorbed. So what happens is that this quantum interaction, where because it's the right wavelength and it has a match between the right molecule, that energy comes in and it excites the molecule. So what happens is that energy coming in at one wavelength, there's a lot of steps that can happen, a wide variety of what could happen, but at the end of that process, you have a molecule with more kinetic energy. Like the CO2 molecules are like this, and if it gets some energy at the right wavelength, it'll start flapping more, it'll start moving up and down more, it'll start translating left, right, and center more. And that is an increase in kinetic energy. And the way that this kinetic energy of molecules works is that it results in an increase in temperature. So at the end of this whole cascade in these interactions, you actually have, to make a long story short, short waves in become infrared. Waves out. Because this energy is absorbed, all those molecule interactions happen, and instead of being some, the same wavelength coming out, after all those interactions, the mechanism where this energy is being stored and then emitted back is through infrared radiation, which is longer than here. It's like a mismatch. This is actually out here, something like this. It's long waves out. Just by the nature of the interactions. It comes in at a certain wavelength. Depending on the molecules, it can match up with one of these wavelengths. And then once it matches up, it heats up at the end of this interaction. And because it heats up, depending on the temperature, it emits this infrared radiation. And so you can do an energy balance where should I do it? So 1 minus RP, so long waves out. Okay, so let's do it here. Solar constant is FB. About 1370 divided by 4, but from the geometry. So, what we're saying now is that these long waves out gives you a relationship where this flux of the long waves can be quantified by their temperature raised to the 4th and the Boltzmann's constant. So this can be the flux here. And then what we're saying is what comes in is 1/4 of S naught. This was integrated to be 1370, giving us the solar constant. But if we divide it by 4, that's what comes in. But then only a fraction of that gets absorbed. Some of it gets reflected by the albedo. So if we do the energy balance, it's the solar constant, which is the area under this curve, divided by 4, because that's the geometry of the interaction in terms of a cross-sectional area versus the surface area. Then some of it gets reflected back. So that would be the energy coming in. That gets balanced with the energy coming out. So this would be in is out. So if this is balanced, they're balanced. So this would be, as we defined it, the temperature of this system here. So this would be the average Earth atmosphere temperature. based on this balance. So that is not as complicated, and I mean, that's just considerations of black body radiation, what comes in that's measured, fit it to the black body curve, and then the geometry of this, some of it gets reflected. What comes in is the amount that does not get reflected with the incoming solar radiation. Only a fourth of it faces the sun. We use Stefan Boltzmann radiation law, and that would allow us to define a temperature. Okay, so that's cool. So what is the solution to that? Well, we have all we need to find the numbers there. So if we use this albedo of 0.3, global average of 0.3, so TO equals, let's get two different scenarios here. So if we plug in this 0.3, it's pretty cold. So that's pretty cold, but it makes sense in the sense that if we've ever been in a plane or if we've seen like movies of hot air balloons and such, as you leave the surface, the atmosphere is really cold. It is really cold as you leave the surface, or if you look at those charts of elevation properties in the sky, it gets very cold as you leave the surface. So that's included in this system. There's gases still there. That's part of the energy balance. And then if you go to the poles away from the equator, that also is cold. So that's why it's not zero, it's not space. Space, by the way, so this is what we were saying here, based on Planck's law, this is 577 K, this is 3 K. It's known that space is super cold, almost absolute zero. So now we're saying if the reflection is 0.3, then the average temperature of this whole system is 255 Kelvin, which is cold, and which makes sense because the atmosphere is cold as you leave the surface, and the poles are cold. And even in the hottest Sahara Desert or Death Valleys of California, that's only like 50 Kelvin. So that's like 100 degrees, 50 Celsius, so like 320 Kelvin. So that's not even a variation of 100 in the highest things. So that kind of makes sense as a global average. But if we were to give a little more range, if we were to say if RP, if there's less reflections, let's say, for example, less clouds. Less clouds would be less of the major source of reflections. Then that means there's less getting reflected. So this number's bigger here. So you would get 268 Kelvin as the energy balance. So a little bit warmer. But what's known is that it's been some methods and assumptions, but there is a value that people have measured. So they said if the Earth has a finite temperature at an average, and we know this is long wave infrared radiation going out, then they've defined that in measurements and assumptions to be 370 watts per meter squared of this long wave out. So we said this. Long. And so assuming that if we take this more measured, the actual from data, that would give you a T naught of 288 Kelvin. So pretty warm actually. That's 15 Celsius, which is pretty much San Diego on a super cold day for us. So those are some values of this energy balance. And so this is the energy balance. And here's some values taking these assumptions of saying that a typical accurate, I mean not accurate, but considering all of these typical values of the type of composition of molecules, the amount of clouds, some particles that are known to float in the atmosphere as aerosol, and the surface reflections, 0.3 is a reasonable answer. And in extreme case, if this cloud contribution significantly decreases, which is less realistic, it'll be a little bit hotter. But what this value here tells us here is that there's other sources of not necessarily reflections. It is partly reflections, but also that the interactions, this long wave radiation, has there's like feedback. There's another factor called feedback, where due to like the way that things start, it can have a cause and effect, which would perturb the balance somewhat. So if we were to say that the net radiation is the balance between the force of the sun, the flux of the sun, minus the long coming out, this is in, this is out. That's zero at equilibrium. Thermal equilibrium, then we can define another way to quantify this. So this is one way to kind of look into how this balance works, and net would be climate change. So there's some natural and human reasons why each of these terms can change. So if the net, this magnitude increases, this gets into a more negative number, and that would increase the temperature. But besides that fact, we can say that each of these has human and natural causes. Like for example, this solar constant. The sun's profile and intensity wavers over the long and short term. Like we can have some short sudden burst of solar activity, up or down. That is a natural thing. Or over long-term trends, this has changed over time in the millennia and geological timescales. That is a natural source that can change. So that's this term here, so the solar constant. It's constant for the most part, but it's not perfectly constant. This is the reflections. As we say, it depends on the cloud cover strongly. So for some reason, if there's less clouds, there can be less reflections. That can change naturally and artificially. Then this infrared long wave out, that can also change naturally or artificially. We can have just this more water vapor due to the weather. That affects long wave interaction, the overall absorption or emissions or passing into space. But one big one is that if this long wave gets absorbed by greenhouse gases, meaning gases that allow this short wave to come in, like a greenhouse that's not actually green, it's clear to our eyes. It comes in as a short wave, and then once those interactions with the surfaces happen, it goes into long wave, finite, it increases the temperature, and that gets emitted as infrared radiation, and then that gets absorbed by the gas, because the gas doesn't like the short wave, but it likes the long wave, and it keeps that energy. Greenhouse gases, like CO2, methane, and water. That is one thing that can perturb this. And then this can be particles in clouds. And both of those you can imagine could be, so particles could be like soot that gets emitted from engines and fires and industrial sources and things like that. So a natural source would be volcanoes. So that can go up and down depending on the specifics of the material. And then what's more complicated is that there's these so-called feedback mechanisms, where because there's more thermal infrared radiation and there's more absorbed, that changes the weather pattern, which changes the clouds, which changes the reflections, and so forth. So that's the general energy balance on how we have this interaction from the ultimate source of energy, which takes on this profile, and we fit it to the black body to get a flux of energy, and then that can give us this energy of what comes in versus what comes out. And lately, it's been in balance for this whole history of the Earth in terms of the development of the atmosphere. After that happened, this balance pretty much has been slowly, it changes, but due to these natural things as we've been talking about. But the biggest disruption to this balance was human activities, which can affect both reflections and long wave absorption. Okay, so that's all I had today. We'll talk next time. See you in the next session.